The transformation begins far from the finished watch. A dense block of gold enters a controlled furnace where
molten gold flows carefully into a precision mold shaped for the future case structure. The mold controls cooling speed and contraction rate.
the cooled block enters a CNC milling machine. A rotating tool begins removing microscopic layers of gold. Sparks appear briefly as specialized tools refine the internal cavities. These cavities must align perfectly with mounting points inside the movement. Under magnification, engineers inspect the finished case half. Surface imperfections are almost invisible to the naked eye. Gold dominates the exterior, but internal components rely on specialized alloys. Brass plates provide machinability and dimensional stability. Metallurgical stability becomes critical once the watch begins operating in real environments. Body heat, sunlight, and changing weather constantly alter temperature.
What appears to be a decorative feature is actually a solution to a mechanical load problem.
Hardened steel components follow. These pieces handle the most demanding mechanical loads inside the watch. Cutting hardened steel requires slower machining speeds.
Synthetic ruby jewels arrive next.
Unlike conventional watches, the Grandmaster Chime uses a reversible double-sided case. This means the watch can rotate within its housing.
Sapphire crystal production begins separately. Synthetic sapphire is extremely hard and scratch-resistant.
Effers. Under magnification, the hinge components are temporarily fitted. Rotation must feel smooth but controlled.
The case now enters the finishing stage. Polishing removes microscopic machining marks left by cutting tools. Case edges receive special attention. Sharp edges concentrate mechanical stress. Over time, these stress points can deform or crack softer metals. Engineers measure sealing channels cut into the case interior. Even complex watches must resist dust and moisture. With the case structure complete, attention turns briefly to the design philosophy behind the Grandmaster Chime. Many chiming watches existed historically as pocket watches, where size constraints were far less severe. The reversible case itself emerged from a practical challenge. Two functional dials required a system allowing either side to face outward. Early prototypes revealed mechanical weaknesses. Hinges wore down too quickly. Case alignment drifted slightly under repeated rotation.
The Grandmaster Chime ultimately became one of the most complicated wristwatches ever built. Achieving this required
The dial begins as a thin disc of brass placed beneath a precision stamping press. The machine cuts and shapes the base geometry. Surface finishing introduces subtle textures across the dial. These textures improve readability by reducing reflections. Dial markings are printed with microscopic precision. Calendar indicators, hour markers, and complication displays must align exactly with internal mechanisms. Luminous compounds are applied to selected markers. These materials absorb light and release it slowly in darkness.
This plate will anchor dozens of gears and levers. Its holes must be positioned with absolute precision.
Anti-reflective coatings are applied to both sides of the sapphire. These coatings reduce glare and improve dial visibility. The finished dial and crystal meet during preliminary assembly tests. The movement plate returns to the workbench under intense magnification. It is a small disc of brass. The mainspring barrel arrives first. Inside the barrel sits a tightly coiled spring, storing mechanical energy. A sequence of gears begins forming the gear train. Each wheel and pinion pair reduces rotational speed while transferring power forward. Each gear pivot sits inside a synthetic ruby jewel. The jewel acts as a bearing surface. The escapement assembly now enters the movement. This mechanism regulates the release of energy from the mainspring. Lubrication follows. Engineers apply specialized oils to pivots and gear teeth using extremely fine tools.
Shifts to the chiming system.
Engineers adjust hammer tension carefully. If a hammer strikes too softly, the sound becomes weak.
Calendar mechanisms begin joining the system. Small levers and wheels track days, months, and leap years automatically. Power reserve indicators are added next. These components measure how much energy remains stored in the mainspring. The movement now appears dense with components. Hundreds of parts interact across multiple layers. The fully assembled movement is temporarily powered. Engineers observe how energy travels through the gear train. Assembly continues in a controlled, clean environment. Even microscopic dust particles could disrupt gear motion. Work surfaces remain spotless.
Tortures. Watchmakers handle components using precision tweezers. Human contact must remain minimal.
Torque-controlled screwdrivers tighten the final screws. Each screw receives a precise amount of rotational force.
Transcription. The hands are installed onto the dial shafts. Their spacing must remain exact.
The sapphire crystal is fitted and sealed into the case. Gaskets compress along the case edge to protect the interior from dust and moisture.
Testing begins immediately. Engineers expose the watch to pressure resistance tests, simulating real-world environments.
Shock testing follows. The watch experiences controlled impacts, replicating accidental drops or sudden motion.
Metals expand and contract slightly. Engineers observe whether timing accuracy remains stable across these changes.
Chronometric testing measures the watch's timekeeping precision across multiple positions.
Engineers record performance data from each test cycle. Minor adjustments follow where necessary.
After testing, the watch runs continuously under observation. Long-term stability matters more than short-term precision. When testing concludes, the Grandmaster Chime rests beneath controlled lighting. The price of this watch is not defined by gold alone. It reflects years of engineering development, microscopic manufacturing,